about their functionality in general and about their implementation on the two different cases or in two different situations on two different kind of systems, on uniprocessor systems and on multiprocessor systems. Here is where we left last time when we discussed about the lock implementation. If you remember, we saw that there could be two kind of locks implementations, the spin lock implementation and the so-called sleeping lock implementation or blocking lock implementation. Comparing with what you have in HAL, they are called lock and mutex respectively, but actually it's not necessarily the names which are dedicated for such functionalities of the locks. So we have spin locks, for which the waiting mechanism is done by using a busy waiting loop, where the lock condition is checked continuously until it is fulfilled, which means until the lock is free. And we have the blocking locks or sleeping locks, where the waiting mechanism is performed taking the CPU from the waiting thread and giving it back, so unblocking the thread, waking up the thread, the sleeping thread, when the lock becomes available. Okay, so that's the idea with the two kinds of locks, and we saw the implementation of spin locks, and now we are talking about implementation of sleeping locks, and that was for the uniprocessor systems. The only difference from spin locks is here when a thread in the lock acquire function must wait for the lock to become available, and here is where the thread is blocked, but before being blocked it must be placed somewhere where can be found later on when the lock becomes available. Okay, and that's a queue, a waiting queue associated with the lock, which you can see is scanned, is checked when the lock is released. Okay, so that waiting queue is checked if is empty or not. If it is not empty, which means there is at least one thread waiting for that lock. A thread from that waiting queue is taken and it is unblocked. The thread block function takes the CPU from the currently waiting thread, from the thread waiting for the lock, and the thread unblock does not necessarily give back immediately the CPU to the thread, but places it in the ready queue. Okay, from which eventually that thread will be given the CPU and resume its execution. When the thread resumes its execution, so after being unblocked, it resumes execution, returning, okay, somehow from that thread block function and rechecking again the lock, and if the lock is now available, takes it, and that's all. Now on the next slides of this implementation, I'm not sure I told you about this, but on the next slides you have some remarks regarding the way this implementation looks like. For instance, why do we need a while here, while maybe someone would expect to be enough here just an if? And logically speaking, it would be just an if here, because initially, if the lock is not available, block the waiting thread, and that waiting thread is unblocked only when the lock becomes available. Okay, so makes sense to not recheck again the lock status, just because only when the lock is available, the sleeping a sleeping thread is unblocked. Still, because if you let me remind you that, just a moment. Oh, Oh, yes, works finally. So if you remember, I told you that in time, the blocking that's the blocking moment. So in acquire function, then when lock release is called, that blocking thread, okay, let's call it TB here, or TW, the waiter. It is so at moment T unblock, okay, let's call it so. So TW is moved from the waiting queue in the ready queue, okay? It is moved from that state, from block state in the ready state, and it is given not the processor based on the scheduling policy, but it's very possible in the ready queue to already be other threads of the same priority, okay, supposing that we use priorities. So in that case, it is very possible to have for the system to have no available processor for that waiter, for that thread, which means that it is placed in the ready queue from where eventually it will be given the CPU. So at one moment, this waiting thread, this blocked thread, or previously blocked thread, now the ready state, become running. Okay, will be given the CPU. But that could be, so let's call it running, the run. So that could be later on than this moment. So in between these two moments, it's possible to have some time interval, okay? And in between these two moments, it's possible for the lock state to change again to blocked, to taken, okay? Because as I told you, if in the ready queue before this T waiter, there is another thread which will be given the CPU before this waiter, and that other thread maybe wants to take the lock also, okay? So calls the lock acquire function. The waiter, this one we are talking about, has no control on the system at all, has no control on the lock, has no control on the interrupts, okay, things like that. So that means that this other thread, which calls the acquire before TW, okay, before this one, could disable interrupts, could be scheduled firstly, could disable interrupts, finds out the lock available, takes it, goes on. And when the T waiter is given the CPU and resumes execution, we can easily see that it's not enough just to go further, supposing that the lock is available, as we expect, because again, I insist on that, that thread in our example here, this one was unblocked this moment just because the lock became available, okay? So logically, we expect to go on from that point, sorry, okay, not checking again the lock. But as I explained you in that scenario, it's possible that between these two moments, the unblocking moment and resuming the execution, okay, so between this one, the lock to be taken by another thread, okay? And that's the reason we have a while here, okay? And there are some other remarks which are described here on those slides. I wouldn't insist on them anymore. I will let you take a look at them at home because I want to give you some details about the way sleeping lock, blocking lock, okay, is implemented on multiprocessor systems, which is not so easy as maybe again we could expect. Let's identify the core part of this implementation, okay? So what we have here is the lock value, which is checked if that lock value is not free. So the lock is if it is free, firstly, it's very simple. The lock is taken. If it is not, we have again placing the waiting thread in a waiting queue, and we have that thread block operation. Okay, so that's the core part. So comparing with this implementation on uniprocessors. But now we have immediately the challenge of how to provide atomicity of this code, okay? How to be sure that if we check the lock and find it out being free, we can take it as in one step, okay? So to have the test and set steps linked together in a kind of a monolith, which cannot be interfered by another execution, okay? So here we have disabling interrupts, masking interrupts for the only processor in the system, okay? That works very fine. But we cannot use the same mechanism here for the multiprocessor systems just because disabling interrupts works on just one processor. All the others could run in parallel, competing the current one, the one where the lock acquire function is executed. Okay, so the question is here. Just let me take my pencil. So the question is how that code, okay, so this while, this waiting queue, append waiting queue, this thread block, this lock, so these are the main operations here, are executed atomically. The problem is that we don't have any mechanism which could provide us atomicity. And what you can note here immediately maybe is that in the implementation of a lock, of this sleeping lock, okay, we have a spin lock, and that spin lock is taken here and is released here, okay? So for providing protection, okay, so pay attention that I don't say atomicity, because using a lock you don't have atomicity necessarily. You have a kind of atomicity, but that's in the form of a mutual exclusion. Okay, so to provide protection, okay, that kind of atomicity that we need, we should use a spin lock. There is no other way to do that. Okay. So that's the first interesting thing, maybe unexpected thing regarding the implementation of sleeping locks, that for their implementation, we need the other kind of lock, the spin lock, okay? Just because the spin lock must not release the CPU while waiting for the lock, okay? For that lock, for the spin lock, okay? If we need to release the CPU, okay, as in that case, we have to firstly, before that, append, place the thread in a waiting queue. That waiting queue must be protected. That's the first data structure that must be protected, not to let more threads working on it. Okay, being it in lock acquire or in lock release. You see, there are multiple places where that waiting queue is used. So we must protect this waiting queue, but it's not only that waiting queue that must be protected. As I told you, these different steps, the checking and the decision being this one or this one, must be linked together. And there is no way to do that but using a spin lock. Okay, so that's the first remark to note here on that implementation, that implementing a sleeping lock, we need a spin lock. Okay, that's the main part, but that's not enough, because let's take a look on this branch when the lock is not available. Okay, when the lock is not available, the thread must be placed in a waiting queue, then must be blocked. But another question is what to do with a spin lock, because if that thread goes to sleep, okay, waiting for our sleeping lock, for that lock, but keeping the spin lock, so the associated spin lock, that gets into a deadlock, okay, because this one will go to sleep, not running at all, waiting for the CPU, okay, waiting for the CPU and waiting for that lock to be released. But the lock holder, which we expect to call lock release and to release the lock, okay, must take the spin lock for this, okay, because in the lock release function, the spin lock also protects the lock variable, the waiting queue, links that operations together, okay, all that we discussed about here. So needs the spin lock, but if this one is sleeping, keeping the spin lock, then we have the deadlock. This one, the waiter, okay, waiting for the holder to release the lock, but the holder waiting for the waiter to release the spin lock, okay? And that's not good. That's why you can see that this protection spin lock is released, okay? Is released before the thread going to sleep, okay? Good. That sounds pretty simple, just not to forget to release the spin lock before going to sleep. But now we have another problem. If we release the spin lock here after appending the thread to the waiting queue, but before blocking the thread, it's very possible to have the following scenario. This one comes, okay, so we have firstly a thread holder coming, finding out the lock available, taking it, going on, and now that holder is between acquire and release, okay? So the lock is taken by this thread holder. And now comes, after a while, this thread, the waiter, finds out the lock taken, is appended into the queue, okay? Intends to go to sleep, so to release the CPU, but before that, we know that thread must release the spin lock. Releases it, but here, before going to sleep, so before being blocked, okay, so here is in the running state, on another processor comes the holder, okay, the holder runs. The holder now finds out the spin lock available, takes it, sets the lock as available, inspects the waiting queue, finds out the waiter there. The waiter is running, pay attention, is not yet blocked, okay? Finds out the waiter there, removes it from the waiting queue and unblocks it. So places it in the ready state, okay? Its structure, of course. So that thread is running, but in the same time, it's placed in the ready queue. But what is more important and more problematic for our discussion is that it is removed from the waiting queue. It is waiting for the lock, is not yet blocked, is not yet in the state that should be for waiting, okay, as the waiting queue state reflects. So it is found there, removed, and that holder releases the lock and goes on. And now this one, even if the lock is available, even if it was awoken, it was unblocked, okay, goes to sleep. Okay, so it blocks. And when it's blocked, it is taken the CPU from it. It is not placed in the ready queue anymore. Now it is not anymore in the waiting queue, and that's a kind of lost thread, okay? Now, of course, we can say, but pay attention because it was unblocked. Now it is in the ready queue. Okay, it is a ready queue and maybe should be scheduled at one moment eventually, but maybe that's not consistent. I know maybe it runs, but what to do with it? So it's not very sure that that thread will get into a consistent state. Okay, but however, what we could note immediately is that that thread goes to sleep, so it's blocked, even if it's not the case anymore. So the problem was that operation and that one, which logically are just one, going to sleep, okay, were separated by one another, okay, were not anymore linked together in a kind of atomic operation. That's why you could note here another another spin lock which is used, which is only taken here, which protects a thread going to sleep until it really goes to sleep. It is not visible here, but if you study the code in the hull, you could know that this kind of blocking spin lock, which is taken by a thread before going to sleep, and please note, before releasing the lock protection spin lock, this lock, okay, is taken here. That lock is released only after the thread block is finished. Actually is released only by the next thread scheduled in this thread block function. In between, so until the thread was appended to the waiting queue, and from the moment the thread was appended to the waiting queue and until it is blocked and the CPU is scheduled to another thread, so between these two moments, the thread is protected by this blocking spin lock. And when a thread wants to unblock here a thread, again, is not visible here, but it is. So I place it here. So when a thread wants to be unblocked, that thread's blocking spin lock must be taken before, okay? So actually the thread holder here in our scenario finds out the waiting thread in the waiting queue. That thread maybe is not yet blocked, but in order to be unblocked, that thread must take the blocking spin lock of the thread it wants to unblock. And this is not available until this thread will really goes to sleep, will really gets blocked, okay? And only after being blocked and the next thread being scheduled on that CPU, that's the moment that blocking spin lock is released, okay? So what is interesting here, again, is not visible, so on that side, is that blocking spin lock on the current thread, so associated to the current thread, is taken by the current thread, the waiter, and will be released by the next thread scheduled on that CPU where the thread waiter was running, okay? That's not custom, okay? It's not the usual way to work with locks, because usually the lock is taken by a thread and released by the same thread. Is not the case here. So that kind of lock is actually kind of a semaphore, that lock here, taken by one thread, released by another thread, okay? But this must be done. There is no other way to do that, because again, we have to link together appending to the waiting queue and blocking the thread, okay? And this cannot be done anymore using this protection spin lock here, okay? This is only used to protect the sleeping lock implementation, but this blocking spin lock is used to protect the blocking operation, okay? So I will let you time to study in more details this implementation by yourself. I only wanted to emphasize the main aspects regarding that implementation, and maybe the main idea to keep in mind is that implementation is not so simple as maybe we expected. Okay. Any question here?
I have a question.
Please.
I saw in the HA implementation that before acquiring the spin lock in the mutex acquire and after releasing the spin lock, it also disables the interrupt. I mean, for the whole duration of the function.
Yes, I don't think that's needed. Let me take a look just to be sure that I understand your question. I think I know what you mean, but as long as I remember, that's not really needed. That if you remember, that was needed. So disabling interrupts. Okay, it's here, and let's see where the old state is used. So the old state is here. So that kind of operation only protects the the thread running here to not be rescheduled. Okay, so just to give it a chance to stay here while it tries to take the lock. That's not really needed because, as you can see here, that's the spin lock. Okay, so that's the equivalent of this protection spin lock. Okay, that's the spin lock which is used. You can see that it is taken here. So actually immediately after this disable interrupt. So that's not to provide atomicity. That's optional. Okay, so for the moment, let me say just so it's optional. So what is really needed is taking this lock. You see that lock is released. Is released here before going to sleep. Okay, before the thread block, and that's the case for the thread being not available. And sorry for all this code is from one of your colleague. And here is for where that mutex lock is released, the spin lock is released for the case the mutex, okay, this sleeping lock was available. And what is not available here, so comparing with, just to answer, okay, just to answer firstly your question, that is not needed, okay, just to be very clear, that's not needed. That was an option of my colleague Alex Gurzo, which implemented the hull, but from my point of view, that's not needed. Actually, I'm very sure it's not needed, okay? That's somehow inherited from the spin lock implementation, where, if you remember, we talked about this last time, that was again optional, but was indeed a good mechanism to use, because that disabling interrupts on the processor where the lock acquire function was executed was needed, because if that function succeeded, so the lock could be taken, then the interrupts remain disabled until the lock was released, just to protect the lock holder, the spin lock holder in that case, not to be rescheduled. Okay, just trying to help that holder not to be delayed too much, help it to release the lock as fast as possible, such that to assure the expected functionality of the spin lock. Okay, we somehow define the spin lock as being a lock which, when taken, not being kept for too long. Okay, so for helping the lock holder, spin lock holder, to not keep the spin lock too much, the interrupts were disabled on the processor that holder was running. Okay, so makes sense in that case to disable interrupts, again, not to provide atomicity, but only to help the holder to run as fast as possible, not to be rescheduled. Okay, but in that case, the interrupts, as you can note, are re-enabled when the thread succeeds taking the lock. So that, again, from my point of view, doesn't help too much. Or maybe if someone else has another idea, I noted that also. But again, from my point of view, this is not really needed. Okay.
Thank you. I was thinking about that. If we disable the interrupt during the whole function, when the thread is blocked, the CPU doesn't have interrupt.
No, that's another discussion. I'm happy that you noted that, but let me show you that on here, because it's somehow a clear implementation. So we have the same problem here for the uniprocessor. Okay. So even more critical for the uniprocessor, because you note here the interrupts are disabled here. We can note they are enabled here back. But what happens if the thread goes to sleep? We cannot see here any CPU enable interrupts. And if the interrupts remain disabled for the single processor, that's not good, because that processor cannot be rescheduled, okay, based on the time interrupt. So the big question here is, what happens when the thread goes to sleep with interrupts? Now, is not visible again here, so the implementation must be studied a little bit deeper in relation with more threads, okay? Because if you do that, what you could note, for instance, so what you should take a look at were for instance here the thread. Just let me write with this, the thread yield function. Okay, so that's a possible scenario. So when a thread disable interrupts goes to sleep, okay, here in the thread block, a schedule function is called. Okay, that schedule function basically switches the CPU from that thread to another one. Now let's imagine that other thread which is chosen is a thread in the ready queue. Okay, actually that's the way to choose the next thread. That thread in the ready queue is was placed here because at one moment thread yield was called on its execution. That was the way to force that thread releasing the CPU. If you take a look at the thread yield, okay, is not here. I mean, if you take a look on Pintos, for instance, okay, because that's the uniprocessor implementation, you could note that in the thread yield, basically what happens is the current thread being placed in the waiting queue, in the ready queue, and the schedule function is called. But to provide protection for this operation, especially for the ready queue, the interrupts are disabled, and then after the work is finished here, the interrupts are enabled. But here we have the same problem. Interrupts are disabled by this thread, which basically goes to sleep. Okay, it is in the ready queue, but another thread is run. Now, this thread, which will be the next for our scenario, was placed in the ready queue, and before that it disabled interrupts. Okay, so that thread, I know X, let's call it, is here, and now we have our scenario. The waiter comes, disable interrupts, calls thread block, is rescheduled, the CPU is moved to this one, so now this one is given to the CPU. Okay, that's the CPU, and that one was was suspended in thread yield, and now it resumes execution from that point. And the next step that thread do is to enable the interrupts. So what happens, okay, just to conclude, is with this mechanism is in general that is not necessarily the same thread with disabled interrupts to enable them back. Many times, especially in cases like that, when a thread is rescheduled, when the CPU is rescheduled, when the current thread is suspended. So in many cases, one thread disable interrupts, and the next thread, which is scheduled, enable them back. Okay, so they work actually in pair, not just on one thread. So that's the way interrupts actually are disabled and enabled. So that's the case for any thread which is rescheduled. That thread maybe could be a new thread. You could take a look of how a new thread starts, and you could know that the first step to execute is to enable interrupts. That next thread could be a ready thread, as I showed you. That ready state before going to sleep, before being suspended, disable interrupts, and immediately after resuming its execution, enable them back. Okay, so that's about this mechanism, which again is not visible taking a look only at this implementation, but it's a good question indeed, and that must be clarified indeed. I'm not sure if you understand my explanation.
Thank you very much.
Okay, you're welcome. Okay, and with all these explanations, which took me a little bit more than I planned, I finished discussion about the lock implementation, okay, being them spin locks or sleeping locks or blocking locks. Now, I will skip the other synchronization mechanisms just because their implementation is basically the same, okay, or is using the same mechanism, being them disabling interrupts for the uniprocessor or some kind of atomic operations for the multiprocessor case. So I will skip them. What you have to do, of course, is to clarify their functionality, to remember their functionality, which I'm pretty sure you can do that by yourself. Okay, because now I want to switch to another subject, which is related to your second part of your project. Okay, and where we have a lot of things to talk about. Okay, that chapter, that section I called process management. In your project is called user program module or component. Basically is about what we have to have, what we have to implement, what we have to provide in our operating system to support the user running his or her own applications. So what is needed for running user applications. Finally, that's the main purpose of an operating system, to help the users running their applications. Okay, that's very important. Okay. As I told you, there are a lot of things to talk about in this context. So I will not cover all of them, especially because all these many things to talk about actually is a kind of everything in a system, every resource in the system. Why? Let me remind you what the process is, what the user application is. Just a moment. Okay, so that let's take a look at the definition, which actually I suppose you know. So I'm trying to. Okay, it doesn't matter. So what is a process? What's a user application? Okay, it's said that is an abstract concept. It's the way an operating system models an execution. Okay, so what the users want is to use the computer. Okay, but the computer can use to run something, to execute instructions. Okay, so that's the main functionality of a computer. We want to run instructions on a computer, on a computer's processor. That instructions, okay, form what we call a program. So we want to run programs on a computer because that programs perform something, computations or things like that. And so the way to model an execution is called a process or an application. But as with any other abstract concept or modeling concept in the operating system, we could ask the question, what is model? Okay, what this execution means, or which hardware resources are modeled, are abstractized by the process concept. Obviously, firstly, we could think to the processor, okay? Because that's the main component which is used in an execution. So an application is mapped on processors, on a processor, okay? But for that processor to run something, we know, okay, from the computer architecture design, that processor needs the program to be run, to be stored in the memory, okay? Now, the execution, that process, so needs memory. That means that the process concept also covers the memory, not only the processors, okay? But now, having memory, so having the program loaded in the memory, having that program being given the CPU, we have a running process, running application, but that's not enough for most of the applications. Why? Because if an application has only memory and the processor could only perform instructions, computations which are provided by the CPU. But that's not enough. Sometimes we need to take data from the keyboard, from a file, from the network, and then we have that program must provide output on the screen or store some results in a file or transfer them on the network, things like that. Which all these operations interacts with other hardware devices in the computer which are not the CPU. Okay, maybe could be controlled, but they could function independently by the CPU, which means that a user application usually also needs to interact not only with the CPU and the memory, but with some other resources, physical resources in the system. And that's why the process covers also the interaction with these resources also, with the file system, with the network, with the screen, with the keyboard, and all these other I/O, what we call I/O devices, okay? That's why here in the definition, I mentioned that the process is an abstract concept which abstractizes or models the entire computer. Now, in the context of my introduction, if we think now to a process, to an application, what we have there is an entire computer, okay? We could have memory, we have memory because otherwise that program, that process cannot be executed. We have memory, that process is executed. We surely have at least one processor. If we have more processors in that process, we say we have multiple threads, okay? So we have memory, we have processors, we have access to the screen, we have access to the keyboard. In just one application, basically we have everything a computer has. All the resources, the physical resources a computer has are modeled, are abstractized in a user application, in a process, what we call a process, okay? So because of that, of that abstractization of the entire computer, when we want to provide in the operating system support for running user applications, running processes, user processes, actually all the components in the operating system, or most of them, are implied for that. So the scheduler of the CPUs is implied logically, because the scheduler must decide which processor or processors to give to one process. The memory manager is also involved because must decide which memory to be given to that process when that process is created, or at runtime to allocate dynamically or releasing dynamically memory. So the memory manager is involved in running user applications. That user applications interacting with the I/O devices, the I/O manager is involved. Maybe it's not just an I/O manager, it's the file system manager, is the keyboard manager, things like that. So a lot of components in the operating system are involved in providing support for running user applications. That's why when we start talking about this, actually we have to start talking about many things in the operating system, not only about process manager in component in the OS, okay? So that's why you'll see my presentation is not necessarily a kind of very fluent one, okay? We talk about processes, how they are created, how they are stopped, things like that. We also have to make remarks and to give explanations about how the memory is organized, how the memory is allocated for the process. So we have to talk a little bit about the memory management. Then we have to talk about how the file system management is done, at least in the terms of open files and things like that, okay? We will not cover everything, okay, in relation with what user application support means in an operating system, but there are a lot of things maybe okay, not very logically linked together, which we have to cover, at least to give you explanations you need for your project. Okay, so that was my introduction. Okay, just to understand that the process concept is a kind of a complex concept. Okay, because it models an entire computer. Okay, you know that the process from this point of view is a virtualization, abstractization concepts provide in a user process, user application, something like a computer, but of course is not the real computer. That's why the process concept is a virtualization concept. You'll also note that I will insist on that later on, is an isolation concept, because processes by design are isolated, must be isolated by one another. A user process might be separated by another user process. In the same way, a physical computer is separated by default by another physical computer. Okay, so modeling computers, it's also in this form of isolated processes by one another by default. If they really want to talk to each other, to share some resources, we have to do things similar with real life. We have to connect to physical computers by a network cable or things like that. In terms of applications running on an operating system, we could help them sharing memory, we could help them using pipes for communication, things like that. Okay, but otherwise, by default, they are isolated by one another. Their resources must not interfere with one another. Okay, we will mainly insist on that in relation with the memory. Maybe that's the most important part, to be sure that memory allocated to one process cannot be accessed by another process. Okay. However, keep in mind that the process is an isolation concept. Okay, let's take the break, and I will go on after the break. So we'll hear us again at 9 sharp. I'm back. Let's go on with our discussion about process management in general. In particular, what we are talking about is OS support for for being able to run user applications. Now, as I told you, there are a lot of things to talk about in relation with this aspect, how an operating system provides what and how and what, okay, support the operating system provides for running user applications. But to help you a little bit for your project, so that will be somehow my main purpose for today. I will not follow precisely my presentations on the slides, but I will try to cover, I know, somehow independently a few aspects, which will be the memory management. Okay, so sorry, how memory is organized, okay, for a process. The second one is in relation with syscalls and the memory also, okay. We'll talk a little bit very briefly about the system calls, but we'll get into more details about the mechanism, the system call mechanism next time. Now we'll relate system calls with the memory. Then we'll talk another aspect somehow also related to the memory, which is the structure of the user stack. Okay, actually it's about the main stack of a user process. Okay, that's mainly the context of multiple threads running in the same process. And maybe if I have time, we'll talk a little bit about handles. Okay, handles which are kind of access tokens to resources, to I/O resources in general, to file system, to files on the file system, things like that. Okay, so this will be the four aspects that I'll try to cover today. Now let's take the first one. Okay, the memory structure for a process. So I told you that the process is a concept, is a way, is a mechanism, okay, an operating system uses to model some resources, some physical resources in a computer. And now we focus on memory, okay. So what we have on the hardware level is the physical memory, which I used to call the RAM, okay, the random access memory. So just to be very clear, that's the physical memory. And now we have the operating system, okay? Of course, the operating system as a piece of software is stored here, somewhere inside the physical memory. But what I want to illustrate here is that logically is the operating system which controls the physical memory, controls the way the physical memory is used, and based on this abstractization mechanism or modeling mechanism provides the memory, the unique physical memory, let's call it so, in a different ways for the running applications, for the user processes. So we have here user processes, okay, sorry, processes, the user applications, process 1, process 2, and what we are interested in is how each such a process sees the physical memory of the computer. Now, to simplify the discussion, because I know the introduction could be longer, but if I remember correctly, I talked about this during the operating system course also, so somehow I expect you to have a kind of an idea about things like that. So to simplify the explanation, let's begin with the idea that each process sees its own memory as being the computer's memory, the computer's entire memory, which means that each process sees its memory. So what I illustrate here is what I used to call, if you want, a process memory, but in practice that's, or in the literature, that is called a process address memory address space. Okay, so the space where all the memory of that process could be accessed. Okay, and the memory being accessed based on some addresses. That's why it is called memory address space. Memory address space. Okay, or simply address space of that process. So each process is providing the illusion, okay, that the memory it is given is the entire computer's memory, and sees that memory as starting at zero, at address 0, and going up to a maximum value. Could be 4 gigabytes, or on a 32-bit architecture could be few or more terabytes or petabytes on a 64-bit architecture. Doesn't matter. The specific value it's kind of a maximum. But what is important to understand is that the same view is provided to all the running processes. This process too, in our example, also sees the memory it could have access to as starting at 0 and going up to a maximum, the same maximum, 4 gigabytes, okay? So all the processes are provide this view with clearly is not the real view, is an abstractized view, is a virtualized view, okay? Because physically things looks like that. Maybe at 0, the physical 0 is where the operating system is loaded, goes up to some value, okay, so some limit for the OS. Then somewhere else in the physical memory is the place where the process 1 is loaded, starting from, starting P1, limit of P1, and somewhere else in the physical memory is where the P2 is loaded. So starting from the address SP2 and going up to the end or limit of P2. Okay, so that's the way things are, or things are in the physical reality. Let's call that so. Okay, so which means that somewhere, and that somewhere cannot be but only in the operating system. So the operating system must somehow map the virtual address space. Okay, so what we have here actually is the virtual address space of process P1, and that's the virtual address space of process P2. The way process P1 sees the memory, the way process P2 sees its memory. So that virtual spaces must be connected, must be mapped on their corresponding physical memory. Pay attention that the physical memory of one process does not necessarily need to be a contiguous area, okay, consisting in consecutive bytes. Must consist in different disjoint areas, but just to simplify our explanation, we consider it to be like that, a single contiguous area. So the OS must map those virtual address spaces to their corresponding physical address spaces. Okay, maybe we could call them so, the corresponding allocated physical memory. And this mapping, this correspondence, this translation is done based on some mapping structures. Okay, so what the OS really needs to manage is some memory mapping structures, tables, however you want to call them. I'm pretty sure you remember about paging or about segmentation. Okay, these are not new notions to you, I'm pretty sure. So we'll talk a lot about paging because the paging mechanism is enabled on the system HAL and Pintus also run, so our operating systems run. So the paging is enabled, and we'll talk about paging in details, but for the moment, so in that context, these mapping tables are called paging tables, but for the moment, let's call them in a general way, memory mapping tables, okay? And do not refer to particularities regarding page tables structure, okay? So it's pretty much the same for paging, segmentation, on any other way the operating system could map a virtual view of the memory on its corresponding physical layout. Okay, good. But when we have something like that, we have two kind of memories and correspondingly two kind of addresses. We have virtual addresses inside the virtual address space, a virtual address being basically the offset from the process start of its memory, from its 0 up to the byte it needs to make access to, okay? So that's the virtual address, an offset, and that offset must be translated to its corresponding physical offset, what we call the physical address. So the offset relative to the physical 0, okay? So these mapping tables basically translates virtual addresses to their corresponding physical addresses. But again, if you remember from the OS course, this could be done by the operating system, but in practice, this is done at runtime. This translation is performed at runtime by the CPU itself. Okay, by the CPU working with the memory management unit. That's another hardware component. But to simplify, we say it's done by the CPU because the CPU is the one trying to execute instructions which makes reference to the memory, like I know things like that. Move some address, 1000 some value. Okay, tries to place 10 in that memory. Okay, so that's that move in a program. It's make reference to a virtual address. Okay, so the CPU encounters a virtual address. The CPU must know that's a virtual address. That is not a real one, because otherwise it will try to make access to this, 1000, and maybe that 1000 is here and not here, as it should be. So the CPU must know that it works with virtual addresses, which must be translated to physical addresses, the ones which finally must be used, okay? But the CPU is not the one deciding where the memory of the physical memory of P1 is, which is the memory and where is the memory allocated to P1, to P2, and some other processes in particular. That's the decision of the OS, which means that is the OS loading the physical memory with particular contents, okay, of P1, of P2, is the OS preparing these memory mapping tables for P1, for P2, so differently for each process, but is the CPU using them, okay, for translating a virtual address in a process instruction to its corresponding physical address, okay? So usually that translation is performed at runtime by the CPU. Very rare is the OS, which also must perform translations like that, okay? We'll see examples of that, usually when the OS is handling system calls. Otherwise, when a program runs without needing OS support, runs instructions, okay, like that move, is the CPU which transparently performs these translations, but the CPU must know about these mapping structures. That's why, making again reference to paging, that's why the paging is not only a mechanism used by the OS, but it's a mechanism which is provided, must be provided by the architecture, by the CPU. So the paging must be enabled in the CPU, so the CPU must know that now the memory is accessed based on this paging mechanism. And is the operating system preparing paging tables, but is the CPU using them to translate from virtual addresses to physical addresses, okay? So We talked about things like this, if you remember, during the OS course. And again, this year, during this course, we'll get into more details about this. But for the moment, please keep in mind these aspects that, so just to conclude, each process sees its memory as being the entire computer's memory. So starting from a zero going to a maximum, which is not true. That's a virtualized view. Okay, that's why we call that memory of a process a virtual address space. This is consistent for all the uniform, consistent for all the processes. So each one sees the memory, its memory like that. But internally is the operating system which prepares the mapping tables, the memory mapping tables, to map the virtual address spaces to their corresponding physical address spaces, and is the hardware, the CPU, which makes use of this mapping tables, but is the operating system, sorry for insisting on that, is the operating system which keeps them updated, so organize them and things like that, okay? What is not shown here, but and maybe should be, is that the operating system itself, when paging, when virtualization, memory virtualization is enabled on the CPU, so let's call it paging, the OS itself, when running, must be run using paging, which means that even the OS itself is between these processes, seeing its memory starting from a zero and going up to a maximum, but this is a virtual view of its memory, and the OS itself must have its own mapping tables, which must map its memory on its corresponding physical counterpart. Sorry. Now we'll see immediately that is not exactly that way the OS is limited. Actually, the OS memory should be mapped to be the entire physical memory, okay? Makes much more sense because we expect the OS to have control of the entire physical memory. But for the moment, at least keep in mind that even the OS when running uses virtual addresses, which must be translated to physical addresses. Okay, I should admit my picture is awful, but I hope that you understand the ideas behind that awful picture. Okay, that's the first thing I wanted to explain you in relation with the memory a process is allocated. Good. Now the second aspect was about syscalls. Syscalls. Okay, what a syscall is. You know, a syscall is a mechanism which must be provided by the operating system to user applications to make the physical resources accessible to those user applications, okay? We can draw here the classical picture of the OS laying above the hardware, so making it inaccessible, invisible to the user apps, okay, user application, so what we call from now on a process, user processes. But finally, the user applications need the hardware, needs CPUs, need memory, needs keyboard, screen, and so on and so forth. Okay, so the OS finally must allow somehow user applications to make access to the hardware, but not directly. Okay, this is not allowed, but asking the OS to do that on behalf of user applications, so providing them controlled access to the hardware, it's something that we expect to be provided. And this kind of controlled access is provided using or through an interface. The OS provides the user applications an interface and the mechanism which is called syscall, the call to the operating system. Call the OS, ask the OS to to perform something on behalf of the user application making that syscall. Okay, the syscalls basically looks like calling the OS like a normal function, but I told you about this other time and maybe indirectly today on the previous slide. This direct call is not possible just because OS and user process runs in different memory address spaces which are not visible to each other. Okay, using that mapping tables I told you about this. Okay, not to consider there in that example the OS. So this process memory is mapped here. This process memory is mapped here. They are not interacting. They are not intersecting to one another. Okay, so they are disjoint by design. Okay, and now considering this one to be the OS, is not possible for that process to make a call here. That's not possible at all. Okay, by design. So that's why system calls are not like function calls. They cannot be so. The only mechanism is a kind of an interrupt. Okay, is a software interrupt. So at the basics, a system call is very similar with a software interrupt. The user application is running, so the CPU, so in the hardware, the CPU is running here, but at some moment it is triggered a software interrupt, and by design interrupts suspends the current CPU execution and switches it in some other place. At some other place, of course, must be configured to be the CPU. So the CPU, when an interrupt occurs, switches inside the operating system. So that's the mechanism to call the operating system, triggering a software interrupt. Actually, on legacy systems, that was precisely the mechanism used to implement a system call, making access to software interrupts. On modern computers, nowadays there are dedicated instructions. So instead of having int and some number, we have instruction like syscall, sysenter. There are different kind of such instructions. But the idea is that we are provided by the architecture with a dedicated instruction to trigger a software interrupt. Okay, kind of exception if you want. You'll find out on the slides that the system call is very similar with an exception, because it's triggered by the running program. Okay, so the system call is a mechanism like that, but I will not insist too much on this. Next time I will explain you the different layers syscall implementation must pass through. But for the moment, we only have to understand that user applications need to use system calls, just because that's the only way to have access to the hardware resources. Okay, that's the only way to write something on the display something on the screen. That's the only way to write something on a disk. That's the only way to create a new application, to create a new thread, to allocate memory, things like that. Everything that is managed by the OS is accessible through system calls. Okay, and now I will make another. I'll take another table for the same subject, syscall. We have an application, an user process, making a system call. And that's the OS. And now, while handling the system call, the operating system must make access to the user memory. Don't forget, I insist on that. Sorry for insisting too much on some things, but I want to be very sure you understand them. Don't forget that theoretically, the OS and a user process view the system memory in different way, and physically these two views are disjoint by one another. Okay, so if we have a system call like this, read from a file descriptor in a buffer 10 bytes. Okay, that's kind of a Linux-like system call. So read from a file which is indicated by this parameter 10 bytes from the current position. Okay, that's something that is managed by the OS. But what is interesting for us for the moment is this buffer. That buffer, okay, that's an address, it's a pointer. That pointer is a memory address, okay? Which kind of memory address? A virtual memory address, okay? So this buffer actually corresponds to a memory inside the virtual address space of this application, of this process P1. And here is VA of buff, okay? And here is where we want the 10 bytes from the file to be stored. Now, indeed, that must finally be stored somewhere in the physical memory. So that's the physical memory allocated to P1, and that's the physical address of buff. Okay, and we have here the memory mapping tables, okay, which could be used to translate this virtual address to its corresponding physical address. Okay, good. So when the system call is performed, one parameter of that system call is a virtual address inside the calling process. That virtual, but now, based on the system call mechanism, the CPU, so the CPU was running here, but now the CPU is running here inside the operating system. And while the operating system is run, so these are the mapping tables of P1. Here are the memory mapping tables of OS. So these are now used by the CPU. Okay, so any memory reference used inside the OS, if you have a VA in OS, is translated to its corresponding physical address in OS using those mapping tables. And now the problem and the question is, what about this VA buffer address? Because the OS takes it as a parameter. It's just a value when it is transferred from the user application into the OS. Is not something which is used when the system call is performed. It's only an information transferred as a parameter on the stack, on the registers, doesn't matter. Okay. But finally, when handling that read system call, the operating system encounters that address, VA buff. If it uses it like that, so making access to the file, okay, the file is somewhere here on the disk, okay, here is the file, reads the 10 bytes. If it tries to store those 10 bytes using directly VA buff, normally this VA buff is translated correctly to its corresponding physical address using those mapping tables. But don't forget, currently the CPU running inside the operating system is using those mapping tables. So that VA buff, if accessible as it is, okay, in a kind of a move, will be translated through this mapping table, and maybe will be located here and not here. It should be. So we have a problem here. So it's not possible for the OS to just take that VA buff and use it as it is. So which are the solutions for that? Okay. So now I illustrated, I explained the problem, the challenge, okay? Now let's see the solutions, because there are more of them, the solutions. The first one is based on the aspect, on the fact that the OS controls everything.
including configuration of those mapping tables. Actually, I told you about this. Is the OS preparing and updating, keeping those tables updated? So is the OS controlling them? So it's very easy for the OS to make changes in those tables such that to be able to have access to that physical memory. And one solution is to map the physical address buff in its virtual address space, the virtual address space of the OS. So the OS is running here. Normally, we think that the OS using its mapping table sees only its own allocated memory, but it's not necessarily only the case. Maybe configuring that mapping tables, it's possible for the OS using a VA buff, okay? Let's mark it with a star just to understand it's maybe different as a value by this one. So it could choose one VA buff star to map it using its own mapping tables on the physical address it wants to have access to. It's very possible because, again, the OS controls those tables. Okay, so one solution for using that value is to inspect the mapping tables of that process to see which is the physical address, that virtual address, which is given as a parameter here. Okay, so the OS must work with which is the physical address that virtual address is mapped to. So the OS inspects those tables and finds out that value. And after that, configures its own memory mapping tables to have a virtual address. So somehow goes further to have a virtual address buff star, which is in OS, okay, in the OS virtual address space. And now the way to store the 10 bytes in where they should be stored, the physical memory, is to use VA star buff instead of this VA buff. This VA buff is specific, or it works in that process virtual address space. This VA star buff works in the operating system's virtual address space. Okay, so map a physical address into the virtual address. This is possible because, so just to make a parenthesis, which will be clarified in more details when we talk about paging and memory management. This is possible because in a virtual address space, that space is not entirely used when we start the process, being it the OS, but only parts of it are used. Okay, so some parts are mapped to the physical memory, to some content in the physical memory. So this one which I hashed here, but some other parts are not mapped, are not used. So there are some gaps, some holes in a virtual address space, which can be used for mappings like that. Okay, so find out a gap here, choose a VA star buff in such a gap and map it on a physical memory content. Okay, and now this part of the virtual address space becomes also hashed, so being in used. Okay, so because of this sparse structure of a virtual address space, it's very possible to do something like that. After using that memory of that process, okay, the operating system could unmap, okay, that VA space, that VA address from its corresponding PA address, just because that's not the memory the OS normally uses. It's not its own memory, it's the memory of another process. But that's a solution for the OS to make access to the memory of the other processes running in the system. Okay, that's a kind of a solution you could find out to be used in the how. Okay, any question related to this aspect? Okay, I'm glad to say that's clear to you. Now let's go on another board. but talking about the same problem, okay, which I call generically syscalls. So we are talking about solutions, okay, a second solution which works in particular cases, okay. So that other solution helps the OS access memory of currently running process. So the process which has just performed the syscall. So let's illustrate again. Here is the physical memory. We have the memory mapping tables of P1, which maps its virtual address space to its corresponding physical memory. So here is the physical memory allocated to P1. Okay. So when the CPU was running that application makes or made a syscall, and that syscall switches the CPU, okay, inside the operating system, starting handling that system call, okay. That was the currently running process. That's the process on behalf of which the OS is running, handling the syscall, okay? So just to clarify the context. And now this second solution helps the OS access the currently running process in a much faster way than the previous solution, mapping physical memory inside the operating system virtual address space, and when finished with accessing that memory, unmapping it, okay? So this is done in the following way. The virtual address space of a process does not only maps or is not entirely mapped on the physical memory allocated to that process. Actually, I told you before that only some parts of that virtual address space is actually are mapped on physical memory, because from the, I know, even taking the 32-bit architecture example, for which the virtual address space size is 4 gigabytes. So even for this kind of limited architecture, for those 4 gigabytes, we don't have so many or too many processes, running processes using entirely 4 gigabytes. Okay, that's very clear for you. I guess. We have processes using a few kilobytes of memory, few megabytes, but very often processes using gigabytes of memory, okay? 4 gigabytes. So which means that from the entire possible accessible address space, virtual address space, physically only some parts, small parts are actually used, allocated and loaded physically, which means that such parts are in use, but there are a lot of gaps, a lot of holes in the virtual address space which are not mapped. Okay, so these mapping tables are not so simple as illustrated here. Actually, they are able to map only parts, okay, in the physical address space. Okay, this one here and this one here. Okay, so we have gaps, we have holes. Such a hole, usually a big one at the end of the process address space, is used to map the OS. Sorry. So using the mapping tables like that. Now let me make another picture just to make it more clearer. So we have the process, its virtual address space, and that virtual address space is divided in two parts, okay? And inside the OS, we have, now I make it larger, the memory mapping tables, the paging tables for paging, and we have here the physical memory. And let's consider that the process is using entirely that part, okay, just to simplify a little bit. So this part of its virtual address space is mapped using that mapping tables of that process on the memory allocated, physical memory allocated to that process, okay? But let's consider the OS here just to simplify, okay? But the other part, this part of the at one end of the process virtual address space is mapped on the OS. Okay, so what we have here in the same virtual address space of a process, of a user process, is the process itself, its memory, and the OS. So here is actually the memory of P1, and that part is the OS. First problem, or the first challenge which must be faced here is how the isolation of the OS from the P1 is further provided, because it must be provided. But that's a challenge which we'll address when we'll talk about paging and memory management. It is possible, okay? So isolate, actually protect OS from P1, okay? And now the second aspect, which is what we are interested in. If we have something like that, the CPU running the user application when encounters a syscall. So the CPU when running user application is instructed to use those mapping tables of that application of P1. When encounters a syscall and switches its execution inside the operating system, the mapping tables are not changed anymore. They remain the current one, the ones of the currently running process. Which means that now, when the CPU is running OS code, when it encounters a VA OS, okay, a virtual address in that part of the process address space, okay, here, so that's VA OS, that will be translated using the current mapping tables on its correct corresponding physical address. If the OS, the running OS, will try to make access to virtual addresses inside the P1 part, okay, so a virtual address here of that buff we talked about previously, it will use the same mapping tables, which will correctly translate that virtual address to its corresponding physical address, okay, of P1, where that buff is physically allocated. So when we have a configuration like that, it is common, it is normal, it is by design, okay, that the OS could run and make access to the current process, okay, the process on behalf of which actually the OS is handling the system call, make access to that process memory naturally using the current page tables. Page tables, which are the page tables of the current process, but which have, or which has as a particularity, the fact that they also map the OS, not only the process memory. And now to generalize a little bit, so the same problem here, P1, P2. Okay, here is the OS logically speaking, but in the physical memory, we have the OS, we have P1, we have P2, and now we have memory mapping tables of P1, memory mapping tables of P2, and we have P1, OS, P2, OS, which means that this part is mapped here. This part is mapped here. This part is mapped here. This part is mapped also here. So the OS is shared, okay, you can see, among all the processes, between all the processes in the system. In that way, mapping the OS in at one end of each process virtual address space, okay? So just to conclude, that helps the OS make access to the currently running, okay, is not running, but you understand what I mean, the process which trigger the currently handled system call, okay? So this helps the OS making access to the currently running process memory naturally, directly using the current mapping tables. Now, if the OS handling a system call from a process P1, from some reasons, wants to make access to another process memory, that kind of mapping table structure does not help anymore, okay? In that case, the only solution would be the previous one we talked about, to map the needed physical address inside the OS virtual address, just to be able to make access to it, okay? So, but otherwise, this structure helps the OS make access to the current running process memory very fast, okay, without mapping, unmapping memory addresses. That's the way you will see HAL function. So using the same mapping tables for both a process and the OS. So somehow the OS doesn't have its own mapping tables, or in other words, the mapping tables of the OS are appended to all the mapping tables of all the processes, okay? So maybe there could be some kind of mapping tables for the OS, but they are appended to the mapping tables of all processes in the system, okay? So anyway you want to say about this. There are some other aspects, okay, how the OS memory looks like. So it's not the OS mapped only on its own physical memory. Usually is the entire physical memory which is mapped here, but that's a detail that we'll talk about when we'll talk about memory management. For the moment, I only want you to understand that the OS is mapped inside each process virtual address space. That used to be a very common mechanism, but in the last 3 years, that was also a problem. So just to anticipate something that we'll talk about from the security perspective. I told you that we have, or there are mechanisms, there are hardware mechanisms to protect the OS from the P1, because pay attention, when the CPU is running inside the process, that process could easily try to make access to addresses here. They belong to its own virtual address space. Still, the CPU must know that that kind of address is an attempt to make access to the OS and to block them, okay? There are hardware mechanisms to provide protection for that, but in the last years, there were some design flaws discovered in processors. The Intel processors were among such processors, which allowed an attacker to break this protection and to make access to the operating system memory from a user application, which was surely not something good. And in the modern operating systems that currently running OSs, real OSs, we don't have any more precisely something like that. but HAL is a little bit behind, and we still have that very used technique to map the OS inside the P1. And again, we'll talk about the security aspects and the new way to organize the process virtual address space in more details later on. Okay, for the moment we have to, that was all for today, we have to stop today. I covered only 2 from the 4 announced problems. I don't even see them anymore. So next time I still have to cover aspects regarding the way the user space stack must be organized, must be provided the command line parameters, something that you have to deal with in your project, and also to okay, we still have to talk about memory accesses. Okay, we have a lot of things to talk about. So for the moment, sorry for yes, here is where I want to be. I want to give you the password for today's lecture attendance. Just 1 more minute, please. That's the one. So here you have it. 1GENC7. Don't forget to use it for marking your presence for today. Keep it for yourself. Thank you for attending the lecture, and wait forward for the next time to meet with you. Bye-bye.
Great day.